All right, here's one more example for class 14, rigid body kinematics for velocity. This is a more complicated problem, and I decided to change it up. I previously had posted in past years a solution where I used the vector notation. That was like 2 years ago. I decided to redo the problem using the 3-diagram method. So we have this piston, and it's constrained to move horizontally, right? So it's going to move this direction either back and forth, and it's attached to a connecting rod BC and a crank AB, right? So if you can imagine, this is a weird-looking engine, but this would be like the crankshaft would be AB, and the connecting rod, sometimes called a con rod, would be BC, and then this would be the piston right up in here. And we know that the crank moves counterclockwise at 4 radians per second, about point A. And at this instant, we want to find the magnitude and direction of the velocity of point C. So this is sort of a pretty practical and type of scenario that we'd want to use for a velocity analysis. So the first thing I want to do is, because I know what's happening with this crank, is I'm going to look at that part AB. Now, you don't have to do a 3-diagram method for something that's in pure rotation. There's no translation, there's no second diagram, therefore the first diagram and that far right diagram are the same diagram. So we will just draw that one in there. And so we know from this thing's rotation being like this right here that it's going to have a velocity right here, and that's going to be the velocity of B. We could also say that that was equal to the velocity of B with respect to A if we wanted to be thorough, but we know that that's going to be the same thing because A is not translating. And we could just, from observation, say that's going to be omega AB and R B with respect to A, which is the same thing as the length LAB right up there. So all we're saying is it's going to be 4 radians per second times the length of this, which is 0.15. 0.15. So that's going to be equal to 0.600 meters per second, just putting on some sig figs there. Something we would want to know about this is the angle that's formed, okay? So we know that this angle right here is 60 degrees. So taking a look right up here, we can work out that this right here is going to be 30 degrees right here, right? Gonna make sure that you can work through and find that angle for yourself. So now we want to do the 3 diagrams of link BC. And I wish I had my handy dandy rulers with me, but they're back in my office. Actually, I have like a little thing. So I'll see if I can make a good straight edge right here and make a good 3 diagrams right there. So I want to try to capture that angle if I can carefully. Because that's going to, making this diagram very carefully. Actually, I'd like to make that parallel if I can, in about the same size. There we go. Okay. And there's our 3 diagrams. Labeling the velocities that we have up here. We know that the velocity of C has to be horizontal, and we know the velocity of B, right? So it is kind of down like that right there, right? It forms a 30-degree angle right there, so we might want to sketch in lightly that 30 degrees. So we'll put that into place right there. Oh, it gave me a little extra little bumpy thing. right there. So that's that 30 degrees, and that's the velocity of B. That's the velocity of B right here. And one more time, right in there. Okay. It's kind of close. Ooh, what happened there? Come on. Damn. Centered. What are you doing? All right. Sometimes, yeah. And this is the velocity of B. Now, because we're using B as the reference, we will constrain it right here. So it gets constrained right there. Boom. And now it's going to rotate, and in pure rotation here. And that velocity is going to be perpendicular there. And that doesn't quite look perpendicular to me. So let me fix it. Perpendicular right there. Boom, 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 boom. Okay. Along that line. And our question is it to the left or is it to the right? Right? Is it going to rotate clockwise or is it counterclockwise? Well, what we want to look again back is because we're concentrating onto this spot right here, right onto the piece. That's our focus when we write the equation for the thing. When we say the velocity of C, which is what we want. Velocity of B is what we know, and we're adding the velocity of C with respect to B to it. So what should jump out at us is that the velocity in the y direction has to be 0 when we're done. So let's take a look at what happens in the y direction. All right. I just made a double dot. I don't know why I did that. And the y directions. That's where I meant to put the dot. So we want it 0 to be equal to, well, here we know it's going to be a negative VB, which is, we actually know the value of that. So we can actually put the value in. There's no reason to keep it as a symbol right in there. 0.600. Right, but only we know that that's 30 degrees right there. So it's only going to be the sine of 30 degrees. Okay, so in order for this to be 0 right here, this one over here on the right hand side has to be positive. Therefore, it has to be rotating clockwise. So the omega BC has to be clockwise. So I'm going to add in, because I don't have enough room over here, I'll come down to here. Omega BC, and we have the length of this right here is going to be 0.2. But we're not done. This is a classic mistake. Make sure you don't make it right here. It's only the component in the y direction. And if you look very carefully at this arrangement right here, we can see you have to make this conclusion for yourself that this angle right here has to also be 30 degrees. Because of that 30 degrees. It has nothing to do with this previous 30 degrees. It just is a coincidence that this too is 30 degrees. It just in this particular position, it's 30 degrees. And you want to be careful, very careful with those angles. So now that too is going to have a sine of 30 degrees equal to 0. And because of that knowledge that the velocity it has no y component to it, and we're using the y, we're able to find out what omega BC is equal to 3 radians per second, and we know that it's clockwise. So now that we have that, by the way, we're able to make the judgment that the velocity of C has to be right to the right, because not only is the velocity of B here to the right, but also the velocity of C with respect to B right here is to the right and up. So now we continue with this equation, and in the x direction here, we say the velocity of C is equal to the velocity of B, which is 0.600, and now the cosine of 30 degrees plus, you can see it up here, that 3.00 radians per second times the distance right here, which is the 0.2 meters, and again times the cosine of 30 degrees. And that's because of this 30 degrees right here. And we're able to find VC is equal to 1.039 meters per second. And I do believe the question was asking for this as well. So those are their two answers, and because I have an arrow right here, that's a vector. So there's a more complicated problem. It's not that really long of a step when you do this three diagram method and break things down into components as we have. So that's example 4. Once again, the only way to be able to get good at these problems is to work through them. Force yourself to work through them, try them out, practice them. Thank you.